Hey friends, it's Miss Adams from Flamingo Math. Welcome back to day 2 in lesson 312. We're still talking about equivalent representations of trig functions. In this section, we're going to study two different categories of trig identities. We want to look at sum and difference identities and then at double angle formulas. We've got those listed here on the first slide. Sums of sine and cosine. We're going to notice the patterns, the different patterns here. If I have the sine of two angles added, notice the pattern has sine, cosine, plus cosine, sine. So we're keeping the plus here. But on the sum of cosine angles, we're going to switch the sign. Same thing, cosine, cosine, sine, sine, but instead of addition, we're going to subtract. And then the differences, sine is going to follow the same pattern, sine, cosine, cosine, sine, but subtraction keeps subtraction, or addition keeps addition. And cosine addition changes to subtraction, and subtraction to addition. So just something to point out. These we'll get to as we move through the lesson, sine of a double angle and cosine of a double angle. So let's jump right in on example 7. We want to find the exact value of sine of 5 pi over 12. So we can do that thinking about the unit circle. If I look at pi over 6 and pi over 4, well, we know pi over 4 is radical 2 over 2, and pi over 6 has radical 3 over 2 for the x-coordinate and 1/2 for the y-coordinate. This is my pi over 6 angle. And we know square root of 2 over 2 is our pi over 4 angle. So this is pi over 4 values. Using our identity, sine of 5 pi over 12 can be rewritten as the sine of pi over 6 and the cosine of pi over 4. Sine, cosine, cosine, sine. That's our pattern. Sine, cosine plus cosine of pi over 6 times sine of pi over 4. So just to recap, if I go back up here, we're using this rule here with the two angles that they gave us down here, pi over 6 and pi over 4. So what's the sine of pi over 6? That would be our y value of 1/2. The cosine of pi over 4 is radical 2 over 2. The cosine of pi over 6 is square root of 3 over 2. And then the sine of pi over 4 is radical 2 divided by 2. So we can rewrite that as square root of 2 plus square root of 6 divided by 4, since our common denominator is going to be 4. You can also factor out a square root of 2 and have 1 plus radical 3 as our common factor divided by 4. So either way would work. Let's try one more. Find the exact value for cosine. Cosine 7 pi over 12 can be determined by adding 1/4 of a pi and 1/3 of a pi. So think back about the unit circle. We know those values for pi over 4. The values for pi over 3 up here are 1/2 and radical 3 over 2. And our pattern for the sum of two angles using cosine is going to be cosine, cosine minus sine, sine. So cosine of the first angle, cosine of the second angle, and then we're going to subtract the sine of the first angle times the sine of the second angle. So cosine pi over 4, cosine pi over 3, minus sine pi over 4 times sine pi over 3. And we get pretty much the same answer as example 7, only instead of addition, we have subtraction. And likewise, you can factor out a negative square root of 2 and have square root of 3 minus 1 divided by 4, or you can leave it like the first way. Let's look at example 9. We have sine of, let's expand that out, sine of pi over 2 minus x. And the sign for the difference formula is sine of the first angle times cosine of the second angle minus cosine of the first angle times sine of the second angle. We want to know, can that be equivalent to the cosine? We know sine of pi over 2 is 1. 1 times cosine. We know that the cosine of pi over 2 is 0 times sine. So we have 1 times cosine minus 0 is definitely equal to cosine. So the cosine is equal to the cosine. Our left-hand expression up here is equivalent to just cosine. So that was pretty easy. Example 10. This one takes a little thinking. Suppose that the sine of an angle is 4 over 5 in quadrant 2. So let's give that a sketch. Sine is 4 over 5. Sine, we're calling that angle alpha. Opposite over hypotenuse. This side is -3. And the sine of beta is a half, and that's in quadrant 1. So beta in quadrant 1, sine is opposite over hypotenuse, which makes this leg square root of 3. So we have two right triangles, one in quadrant 1 and one in quadrant 2. The cosine of the alpha angle, adjacent over hypotenuse, and cosine of the beta angle is adjacent over hypotenuse, and we're calculating cosine of alpha plus beta. So let's write our pattern here. Cosine, cosine, minus sine of the first angle, sine of the second angle. So cosine of alpha, -3/5, cosine of beta, radical 3 over 2, sine of alpha, 4/5, sine of beta, 1/2. We have -3 square roots of 3 over 10 minus 4 over 10, and putting that together, -3 square roots of 3 minus 4 divided by 10. On part D, we're doing sine of alpha plus beta. So the pattern is sine, cosine, plus cosine, sine. Sine of alpha, cosine of beta, plus cosine of alpha times sine of beta. 4 square roots of 3 over 10 minus 3 over 10. Putting those together, adding the numerator over that common denominator. That's not too bad. Example 11, we want to write the trig expression as an algebraic expression using sine times tan inverse of 1 plus cosine inverse of 1. We want to let u be tan inverse of 1. I'm thinking this way. The sine of angle u plus angle v when the sine of u is 1 divided by the square root of 2, because we have opposite over hypotenuse, the cosine of angle u is 1 over square root of 2. Then for this triangle, this second triangle, V, I need this length of this side. So that's going to be 1 squared minus x squared under a radical. So we've got this side is 1 minus x squared. I'm using Pythagorean theorem for that. So the sine of angle V is 1 minus x squared, and the cosine of angle V is just x. So we want the sum of sine u plus v. That pattern is sine u times cosine v plus cosine u times sine of v. 1 over radical 2 times x plus 1 over square root of 2 times the square root of 1 minus x squared. Putting all of that together, we have one messy looking fraction. In the numerator, x plus the square root of 1 minus x squared, all of that divided by the square root of 2, since this fraction is 1, and we have the square root of 2 and the square root of 2 as our common denominator in that case. And then lastly, I believe this is our last example for day 2. We want to find the exact values for the sine of the double angle and the cosine of the double angle. For the sine of the double angle, I'm writing that pattern off of the first screen. Sine of 2 theta is 2 sine theta times cosine theta, and I'm given this information here. We want to draw that picture in quadrant 4. So in quadrant 4, we have a terminal angle here that's at, let's see, cosine is adjacent hypotenuse. So we're 4 units down. We're at the point 3, -4. If this is our angle to get there, that's our theta angle. I'm calling this theta prime. And the sine of 2 theta is going to be 2 times the sine of the triangle, which is opposite hypotenuse, cosine of the triangle, adjacent hypotenuse. We have 2 times 4 times 3, that's -24, divided by 25. So the sine of the double angle. And then the cosine of the double angle, I'm going to use the formula cosine 2 theta is 2 cosine squared minus 1. So 2 times cosine squared minus 1, that's 9 over 25 times 2. So we have 18 over 25 minus 1. I'm rewriting 1. 18 minus 25 is -7/25. That's the end of lesson 2. We have one more to go on this lesson. See you on the last lesson tomorrow.